Hey everyone, let's dive right into this explainer. We're going on a seriously fast-paced journey today, starting from the macro scale of the devices we use every single day, all the way down to the microscopic physics of integrated circuit design. If you've ever found yourself wondering how your smartphone crushes complex commands, or how these massive AI models are trained at literally lightning speed, well, you're in the exact right place.
To really understand why tech giants are completely restructuring their companies to focus on custom AI silicon, we gotta look under the hood. Take a look at this quote from Mac Daily News. Apple actually just reorganized its whole hardware division under Johnny Srouji. And why'd they do that? To forge this incredibly tight integration between their silicon teams and their product development groups. This hardware, software, silicon synergy, it is absolutely critical for speeding up the development of AI-powered hardware. But to really appreciate what Srouji's teams are doing behind the scenes, we first need to understand what they're actually building. And what they're building is mind-blowing. We are officially in the era of ultra-large-scale integration. A single chip inside your laptop, or the phone in your pocket right now, contains well over 1 billion microscopic components. Just think about that number for a second. Over 1 billion individual elements orchestrating pure magic in perfect sync. To put that into perspective, if each transistor was the size of a person, a single chip would hold more than the populations of North and South America combined. It's honestly got to be the most complex manufacturing feat in human history.
Okay, Section 1, inside modern silicon chips. Let's see how engineers actually manage to tame raw physics to build these devices from the ground up. So the foundation of every single microchip relies on basic semiconductor physics. And pure silicon is actually a pretty awful conductor on its own. But by introducing very specific impurities into the silicon crystal lattice, a process we call doping, we create what are known as N-type and P-type materials. N-type gets this abundance of negatively charged electrons, while P-type gets an abundance of positively charged holes. And by carefully arranging these materials next to each other, we gain the superpower to completely control the flow of electricity. Moving on to Section 2, the mighty MOSFET explained. Because to actually control that electricity, we desperately need a reliable switch. Which brings us to the fundamental cell of the modern electronic brain. Enter the MOSFET. That's short for metal oxide semiconductor field effect transistor. As you can see, it's got 4 key terminals: the gate, the source, the drain, and the bulk, or substrate. A good way to think about the gate is that it acts exactly like a water valve. When you apply a voltage to that gate, it creates an electric field that manipulates all those electrons and holes we were just talking about. And here is what that looks like in 3D reality. When that voltage hits the gate, it literally creates this super thin conductive channel right at the surface of the silicon. This channel lets electrons rush from the source reservoir straight to the drain. Take the voltage away, boom, the channel pinches off and the current completely stops. It's basically a voltage-controlled current source, and it is the exact switching element powering everything from your laptop's motherboard to massive warehouse-sized server farms. All right, Section 3, analog versus digital design. Because how we actually use these microscopic water valves completely divides the engineering world into 2 totally distinct disciplines. So the crucial takeaway here is this stark contrast between the two. Analog design, that's the dark art of managing continuous, real-world signals. In analog, literally every physical imperfection matters. Engineers are constantly battling variations in temperature, voltage, and manufacturing just to ensure signal fidelity. But digital design, it abstracts all that messy physical reality into rigid ones and zeros. As long as the voltage is high enough to be a 1 or low enough to be a 0, the exact value just doesn't matter. And this abstraction is exactly what allows digital design to focus on pure logic, tight timing, and massive automated scaling. Let's zoom in on a classic tool used in that delicate analog world, the current mirror. Because analog circuits are so incredibly sensitive, we use current mirrors to guarantee stable performance, even when temperature or supply voltages are bouncing all over the place. They provide these essential bias currents that keep other transistors operating exactly where they need to be. If we look at the schematic here, you can basically think of this circuit as a continuous copy machine. By tying the gates of 2 matched transistors together, we ensure they have identical gate source voltages. And since their physical dimensions and gate voltages are exactly the same, they're physically forced to conduct the exact same current. So we create one highly stable reference current, and then we literally just mirror it out to power the rest of the chip. Pretty brilliant, right? Which brings us to Section 4, bridging worlds with ADCs. Because our physical world, You know, sound, light, temperature is continuous, but our massive processors are discrete. We desperately need a bridge between the analog and digital realms. And that bridge is the analog to digital converter, or ADC. An ADC translates real-world voltages into numbers through a really rigorous four-step sequence. First up, an anti-aliasing filter smooths out the signal, getting rid of any unwanted high frequencies. Second, the circuit takes a sample of that continuous wave at a very specific moment in time. Third, it holds that exact voltage value totally steady. And finally, it quantizes that value, mapping it directly to the closest n-bit digital code. To give you an example, the Successive Approximation Register, or SAR ADC, is a wildly popular, incredibly efficient translator. It works kind of like a guessing game, using binary search logic to rapidly zero right in on the exact input voltage. It does rely on highly precise timing, which is usually provided by phase-locked loops, or PLLs, but because the SAR ADC is so compact and uses such incredibly low power, it's the exact tech that enables things like responsive depth cameras in VR headsets or the high-fidelity audio codecs right inside your phone. Okay, Section 5, from code to logic gates. Once our signal is securely digitized, engineers obviously aren't sitting there placing transistors one by one. They rely on incredibly powerful automated workflows to handle billions of signals all at once. And this workflow operates at blistering speed. First, engineers write out the chip's behavior using hardware description languages, known as RTL. Then, specialized software called logic synthesis steps in, taking that written code and automatically mapping it into thousands or even millions of digital logic gates. But it doesn't stop there. The software then runs rigorous timing analysis to make sure every single electrical signal propagates through the chip before the next clock cycle hits. Plus, it runs massive simulations to verify that the logic is flawlessly correct long before a single piece of actual silicon is ever cut. Now, to prevent these billion transistor chips from literally melting under the massive electrical load, digital logic relies almost exclusively on the CMOS process. CMOS stands for complementary MOS. It cleverly pairs an NMOS transistor with a PMOS transistor. The magic here is that when one is on, the other is completely off, meaning there is no direct path from the power supply to ground. Power is really only consumed during that active switching split second between a 1 and a 0. It is the ultimate energy-saving architectural trick. Honestly, it's the whole reason your phone battery lasts all day, instead of draining in 5 minutes and burning a hole in your pocket. All right, last section, Section 6, the chip manufacturing journey. Let's zoom back out and see how these super intricate blueprints are actually etched into physical reality. Taming that physical reality requires some incredibly meticulous layout and fabrication. We aren't just drawing flat lines here. We're essentially building tiny, microscopic 3D cities. Engineers have to physically isolate the N-type and P-type transistors using structures called guard rings. If they skip this, a phenomenon called parasitic latch-up can happen. That basically creates an unintended electrical short circuit that can permanently destroy the entire device. So yeah, it's a very high-stakes game of physical planning. Historically, this relentless march of manufacturing innovation has taken us from chips with barely 100 transistors back in the 1960s, what we used to call small-scale integration, all the way to the ultra-large-scale integration we have today. We are now routinely packing over 1 billion transistors into the massive GPUs and AI accelerators that are driving today's whole artificial intelligence boom. It's just this staggering exponential curve of human ingenuity. Which leaves us with a pretty fascinating question as we look to the future. Our transistors are now approaching the size of just a few atoms across. So, as we shrink these devices down to the atomic level, what happens when the weird, completely unpredictable rules of quantum mechanics finally break our reliable classical physics models? How in the world will we design the next generation of chips when the very laws of physics we rely on begin to rewrite themselves? It's a massive, massive challenge for the next generation of engineers, and I absolutely cannot wait to see how they solve it. Thanks for joining me on this explainer today, and keep learning.